Wonderful. Thanks for the introduction. So we have quite a few of the authors here in the audience, actually. Mathias, sitting over there from the University in Freiburg. Then Haniel is also somewhere, and Bruno Andreotti from UFMG in Brazil. Andrew Reynolds, Hans-Jörg Schurr, and Cesare Tinelli from Iowa. And then myself, Jibiana, Jakpor, and Clark Barrett from Stanford. Let's talk about the motivation behind this project. And since this is the ITP community, I think I don't have to talk that much about why we want to use Isabelle. Basically, we have expressive language. We have a lot of libraries with formalizations and facts that we can use to reach our correctness proof or whatever we want to do in the system. This system offers us a very high level of trustworthiness. And an example for that is this verified cell-phone microkernel. I love taking this as an example because this is a huge project and it was completely verified in Isabelle. Okay, so the goal behind an interactive theorem prover, though, is that the human has the great, big, creative idea, and the machine handles the rest. And I don't know about you, but I've been in the situation where I had my big creative idea, or at least I thought I had, and I was stuck proving some really unimportant and tedious lemma that on pen and paper I probably would not have even written down or would have just said trivial and moved on. And Isabelle already has pretty good proof automation. You can type in Sledgehammer, and Sledgehammer will then call some external automated theorem provers, including some SMT solvers. Here, for example, it called zipper position, it called vampire, it called SMT solver verity. And then it will learn which of the facts the external solver needed to actually prove the goal. However, since Isabelle is skeptical, it does not want to trust any of these external solvers. So it has to find a proof inside of itself with the facts that the solver used. That does often work, but not always. Maybe hands up, who has been in this situation before? Nice, okay. And this situation is usually the most annoying one because you actually do really want a proof and it's like, oh, CBC5 had a proof and now I can't use it because it times out. So one way to improve on the solver's ability to find the proof on itself, so Isabelle's ability to find the proof on itself, is to have the solver not just give a yes, no answer, yes, I could prove this, and not just give an answer, yes, I could prove this with this facts, but actually give more information by also giving a proof certificate. So a list of steps it did to reach the unsatisfiable result. And the way this works is that the lemma in Isabelle is encoded into SMT-lib. It is given to the SMT solver, and then the SMT solver returns the proof certificate. And I realize now I actually have a laser pointer, so I don't have to just extend my hand and you have to puzzle and figure out where I'm pointing it. But basically here, this proof certificate is then given back to Isabelle, and then it has to be reconstructed. This has been done for both Z3 and Verity. We've just actually seen an example where Sledgehammer suggested Verity to solve a problem. However, we wanted to add a new solver in the same way to Isabelle. And in our paper, we describe what challenges we met and how we had to work in different areas to actually add this new solver, and how it became clear that if we wanted to actually update and maintain the solver and maybe also add other solvers, we needed to make a few changes. Okay, so our case study for adding a new solver was CVC5. CVC5 is an industrial strength SMT solver. It supports many theories. And we have seen some evidence in earlier evaluations that it would be beneficial to have CVC5 being used in this way by Sledgehammer. We did have to make some modification on the solver side, so on the CVC5 side. We had to change some stuff on the Isabelle side as well. And we have put quite a lot of effort into providing some new debugging tools. So if someone now wants to add another solver, they will have a far easier time than we had with CVC5. One thing to know is that adding a completely new reconstruction procedure for a new proof format is expensive. So obviously these proof certificates we've seen can be phrased in different terms. There are a bunch of different SMT proof formats, not like in SAT, where I think most people have converged on a few formats. And the good thing, though, is that Isabelle already supports Verity's output format and Z3's output format. So since it's so expensive to add a new reconstruction procedure, we thought, why don't we just use one of the formats they output? And then the reconstruction should be free, because we could just use the existing reconstruction code. Z3's format is a little coarse, and it is not that well documented. There are some bugs that are still open, whereas Verity's output format has actually developed in its own standalone format called ALET, and it is generic and has a bunch of it has a detailed specification. Also, it has a standalone proof checker, Kakara. So that is the choice we made. So our ideal version here is that we still generate the SMT proof problem, but then either CVC5 or Verity can give a proof, and we just return back an ALET proof certificate. So what do we do now if the new solver does not natively output ALET proofs? Well, one solution to this would be to make the solver natively output ALET proofs. Another one, and that is the one we choose, and that seems more accessible to most solvers, is that you translate whatever proof the solver does output into an ALET proof. You can either do that externally, or you can do it internally. And for CVC5, we did it internally in the SMT solver. We took the internal proof from CVC5, and then we output an ALET proof by translating. And I want to talk a little more about this translation, because of course we did not just claim that this is something you can do, but we also wanted to evaluate if this is actually an approach that makes sense. So CVC5's internal proof calculus is called CPC. And it has more rules than the ALET calculus. And what we have to do is, for each rule in this calculus, we want to translate or give some instructions how to translate a step that uses that proof rule into a step that uses a ALET proof rule. Most rules were pretty easy to translate. So if you see the rule here on the left, in CPC, we have this rule not implies LM1, that if you have not F1 implies F2, then you can infer F1. And in the ALET calculus, we actually have a rule that even is nearly called the same, not implies 1, and it basically does the same thing. For other rules, it was not that easy. And of course, there were 1,000 little engineering tasks to actually make this work and to make this work in a reasonable time and so on. However, even with all these improvements, of course, doing this translation will cost you a little bit of overhead in terms of time and in proof size, because you have to go over the proof again for the translation. We did not actually translate all the steps, mainly because CVC5 and many really industrial strength SMT solvers use hundreds of rewrite rules. So they rewrite the terms, and going in and for every of these, I'm not even sure how many we have right now. 500 is maybe an over-exaggeration, but I would say probably CVC, yeah. Okay, maybe a translation function for each of them and translate them into ALET. And ALET also has a little bit of a different procedure for these. So instead, we actually made use of some prior work of ours, which is this tool Isabelle, which you give a rule in this SMT-like language, and then it automatically generates a lemma in Isabelle from it. And then when you actually have a proof certificate that has used the same rewrite, in Isabelle, this lemma here can then be used to replay that step in the proof. So for these steps, we did not want to add a translation method. And the good thing is that all the proof steps that can be expressed as a lemma could use the same approach, and you would not need to translate them. And the lemma is generated automatically, so you know you have not accidentally done some mistake while translating. Okay, I promised you an evaluation, so let's dive in. We first started using SMT-lib benchmarks. However, we quickly realized that SMT-lib benchmarks are quite different from the goals that Isabelle generates. So we decided to do our evaluation on a benchmark set generated in the 17 previous paper, where the authors took a bunch of Isabelle theories and used this tool Mirabelle to create problems from those. And the way they did that is that they have the same 5,000 problems, but they add more or less facts. So Sledgehammer adds some facts to the problem that it thinks the external solver will need to solve the problem. And we do have a set with where 16 facts were included all the way up to 1024. We compare CVC5's internal proofs, so in the CPC format, with Verity's and CVC5's ALET proof. The first graph here shows for how many benchmarks the solver could solve the problem and find a proof and then print that proof. The teal color is CPC. And first, let's compare CPC to CVC5's ALET output. And as we can see here, the teal colored and the red colored bars are pretty close together. So there are not that many benchmarks that could not be translated. We did set a quite generous time limit here, though. Sledgehammer, in the end, will give a far smaller time limit. When we look at Verity proofs, though, so the green bar here, we can see that there have been less benchmarks solved and produced a proof for in the time limit than for the other two. So this does indicate that it's a good idea to support CVC5 and proof-producing mode in Isabelle. So now I have one graph that's showing something good and one graph that is maybe more negative. On the left-hand side, we have the time to produce the proof in the solver. And on the right-hand side, we will have the average proof size. The thing here to know is that we compared only on the benchmarks that all solvers could find a proof for, because otherwise the comparison would be pretty unfair, right? If CVC5 solves something that Verity does not solve, and then it takes a bunch of time, and that would be part of this comparison. Okay, so going back to the time, on this side, I think the laser pointer is a little hard to see. So basically, the Verity proof takes far longer to produce than the ALET and CVC5 proofs. And we see that translation actually does not cost that much in terms of time. However, when we look at the right graph, we see that the translation does add quite a bit of size to the proof. So the internal CVC5 proofs are far smaller, and the new proofs are pretty big, and usually also bigger than the Verity proofs. There are some optimizations on the CVC5 translation side we can still do. So for example, some of the steps maybe get translated into a bunch of different ALET steps, and maybe we could consider adding a new rule to ALET to make it easier. Or we could use one of these lemmas that I talked about with Cesare. So this is still something we could look into. But in general, we have shown here that you can use this translation approach. And this is a good news for solver developers who don't want to change the whole internal proof infrastructure. So I will plug that into Isabelle. And since it's now producing let proofs, we are done and can move on to the next talk. Yeah, no, this did not happen. Wishful thinking on my side. Okay, so once we had done that, we realized that there were some issues. So the ALET standard was kind of developed at the same time as the Isabelle reconstruction was. So not everything was supported. Partly because Isabelle only had Verity to output ALET proofs. And so not everything that was in the standard, but that was not produced by the Verity solver, was actually supported. Then also only certain problems were generated. One example is XOR. So the translation from Isabelle to SMT would actually never put an XOR in a proof, in a problem, sorry, in an SMT problem. So Verity would actually never have generated any proof with an XOR in it. But once we switched to CVC5 and we actually wanted to work with bit vectors, which is a theory Verity does not support, we got a bunch of XORs in the proof. And now we had to support these. There was also the other way. So there were some proofs supported that were not in the standard because the standard had changed since the time, or the standard was misleading. And it was not really clear because of this what was now expected by Isabelle. And even updating to a new version of Verity, where we made changes because of the translation or because some things were unclear, was not possible without changes. And when we analyzed the problems we had, we did realize that one was that parts of the Isabelle code were pretty coupled. This happened everywhere, but as an example, encoding and reconstruction. So when the reconstruction of Verity proofs was done, the developers only had one instance of the one-point rule to test their reconstruction method on. So what had happened is that they had to write a lemma in Isabelle. It was translated into SMTlib and then solved by Verity. And they had to write a lemma in the way that they hoped that a one-point step would appear in the proof. And this is not an easy thing, and you never know how the solver will solve the problem. To figure out where the bug was, very often you had to go through the whole infrastructure and figure out, okay, is it a translation bug? Is this something that is a parsing thing or in the reconstruction, or was something not added properly to the context? So this made testing hard, and we did came up with some solutions to that I will present in the testing part. Okay, then, and I've already spoken about that, the ALET specification had just been written, so parts of it were unclear and had to be rewritten, and we worked with the developers of the ALET standard to make that happen. For that, also the development of the proof checker helped a lot. Then we had the case, as for example, with the XOR, where new rules were not supported, but there were many more rules where this was the case. Also because we want to support bit vectors, and Verity does not actually, or ALET in that time did not have any bit vector rules in its standard. On the Isabelle side, we did make quite a few changes that we hope will also benefit future updaters and developers that want to add their SMT solvers. And this was a huge team effort because we had to change all the backends, right? Like if the ALET standard changed, we had to change the proof checker, we had to change Isabelle, we had to change the solvers, Verity and CVC5. And this is a lot of different people to coordinate with, and everyone has been awesome. So I wanted to show an example now that we've actually made it work. And demos are always a little bit tricky. Please let me know from the last row if you can read this. Okay, I see some nods, very well. Okay, so this seems like a pretty simple lemma. So basically this says that if I have a bit vector of bit width 3 and it is bigger than 6, then it has to be 7. However, the SMT proof is pretty interesting because it has a bunch of bit blasting steps and a bunch of cool rewrites in it. So even though the lemma maybe seem easy, it is not that trivial. And what happens here is that the lemma gets encoded into SMT-lib. So this is the resulting SMT-lib problem. So this A is not now a bit vec 3, which is an SMT-lib type. Okay, very good. And then we also have the goal encoded as the assertion. Then we invoke CVC5 here. It's called CVC5 proof, but we do just call the CVC5 binary on my laptop here. And then we do get the result, which is this proof. And we do go through all the steps. And then in Isabelle, we have some tactic that discharges all of these goals in this proof here. Okay. So we have seen that this works, and actually was not sure if I had time for that, but I think we're good. I also made the same lemmas, but for a little bit of more exciting bit width, because I wanted to see how big we can get. And as you can see, even the 128 bit width lemma here still proofs and gets checked. So this is nice. I turned the tracing off because, okay, so wait. It does check, but if I print the debugging information, it just takes very long. So I did not actually print the problem here. Okay. Yes, but no, not right now. Okay. One issue we identified with the last reconstruction is that the set of rules is sometimes, so like with the 1-point rule, we only had a single example, but with other rules, we only had a handful, is small. So one of the things we really wanted to figure out is whether for any given proof rule in a let, can all instances of that we see be reconstructed. And for that, we needed to change the testing infrastructure a little bit. And one important tool there, we have many that we describe in the paper, is the check SMT tool, which decouples the encoding into an SMT-lib problem with the reconstruction. So instead of generating the SMT-lib problem from a lemma, we can now just take an external one, give it to Isabelle, and it will use the same reconstruction mechanism that it uses for internal problems. And therefore, we can provide our own problem and our own proof, and I don't know, go through SMT-lib, get all the lemmas, and filter out all the rules that are, all the proofs with rules that we want to test right now. Okay. This is what I do here. I have this test problem, and I have a test proof. And whoops, if I go here, we can see that we see the same thing as with the last proof I showed you. Isabelle still goes through every step and checks that all of them make sense. So these are our results for that. These are a lot of numbers. So basically, what I want you to look at is the number of solved column here and here, which are the ones for which the solver could find the proof. And then the second column here is the number of those that could be reconstructed. So for example, CVC5 alert of 1,327 solved runs, it could reconstruct all but one. For alert, we have 1,305. So there were slightly fewer proofs that could be solved. And then only 1,295 could be reconstructed. We also have this column with uniquely reconstructed, where we show how many of those could not be reconstructed by the other solver. So this shows again that we do want to have a portfolio approach where Verity is still used, and then CVC5 can also solve some other problems that it does, but we do see that CVC5 does give you quite an advantage here. Another thing we do see, though, is that the average time these were reconstructed in is just far worse for CVC5 than for Verity. And this will also be a problem once we start testing more with Sledgehammer. Partly this is because the current reconstruction was done with Verity in mind. And there are certain things like proof compression that are done to speed up the reconstruction. And there are some things we can do there for CVC5 as well in the future. One last testing tool I wanted to introduce that Jibiana, which is somewhere in the audience, worked on. There you go. Which is really useful for debugging, is this new slicing feature in Kakara. You can take a problem and a proof, give it to Slice, and it will generate a new problem and a new proof. And I won't go into details. What I want you to take in is that it's smaller, and it will have the step you wanted to focus on. So let's say I want to look into the reconstruction of transitivity rules. Then I would tell it to slice out step T3 here. And it would give me a new proof that has T3, that's still a valid proof. And then I can check that proof with only that step and maybe some extra step to make it a valid proof. Okay, what have we done? We have worked on the CVC5 or on the solver side to show that you can translate with very little overhead in terms of time and a little overhead in terms of size from any SMT solver that also has this kind of internal calculus into the ELET format. We have very few holes remaining where we couldn't translate or where CVC5 itself does not output a super detailed proof. We have worked a lot on the ELET standard. On the Isabelle side, we have refactored the SMT implementation, so it can now work with different solvers and not just with what Verity outputs. We have shown that by providing a bunch of regression tests. So we have just not tried CVC5, seen that it works, and now the third solver you would add would still break. We have actually added some infrastructure so that you can write regression tests independent of the solver. And we are now supporting CVC5. For bit vectors, we're still working on some of the stuff, but for non-bit vector proofs, we are pretty well there, as you've seen with the evaluation I showed you. And then we have some testing tools. One that makes Isabelle actually a real proof checker, because you can give an external problem. And the slice tool in particular, if you want to only test certain steps. And then a bunch of other tools that you can either read in the paper or, even better, speak to me while we're here together at this conference. Thank you so much for your attention. And feel free to ask any questions.